Welcome to our deep dive into function calling in large language models. Today, we'll explore how these models execute functions and why understanding this process is crucial in interviews. Your ability to explain function calling reveals the depth of your knowledge in LLM engineering. We'll uncover the mechanics at play and discuss how they impact both development and implementation, giving you a clear perspective on this complex subject. Let's discuss the common misconception about how models handle tools and system prompts. While many believe that you simply input the tool name and parameters, thinking the model understands, determines, and decides actions like a human would, that's misleading. These words suggest a specific decision-making module exists within the model. In reality, there's no specialized intent recognizer. The process is more integrated and less about discrete decision points. Let's delve into the core truth of function calling. It doesn't introduce any new reasoning mechanisms. The process involves understanding, matching tool semantics, and extracting parameters, which are fundamentally the same as writing code or translating a sentence. It's all about next token prediction. The model has learned to switch its output from natural language to structured JSON, depending on the context. Welcome to Chapter 1, How Function Calling is Trained. First, we have supervised fine-tuning, which sets the groundwork and formats the triggers. Then, reinforcement learning comes into play, enhancing accuracy, robustness, and handling edge cases. Training is a two-step process. SFT establishes the format and timing, while RL fine-tunes performance. This dual approach explains why models with the same architecture can vary greatly in their ability to call functions effectively.
In Stage 1 of supervised fine-tuning, the model is exposed to thousands of dialogue chains that include tool calls. Training typically involves 5 steps. First, the system lists available tools and their functions. Then, a user might ask for the weather in Beijing. The model generates a structured call, and the tool responds with raw data. Sunny, high 12 degrees Celsius, low 2 degrees Celsius. And finally, the model crafts a natural language reply based on this information.
Today, we'll explore 3 key lessons from SFT. First, it teaches when to switch output modes, using tool calls for real-time info and ordinary text for casual chat. This decision is made probabilistically. Second, it shows how to format call instructions using JSON, much like writing Python. Lastly, it integrates tool results, training the model to convert raw API data into smooth and natural language responses during later training rounds. Welcome to Stage 2, Reinforcement Learning. In this phase, we evaluate several key aspects of the model's performance. Was the correct tool chosen? Were parameters accurately extracted? Did it call when it was supposed to and refrain when it shouldn't? Reward signals enhance accuracy, especially in edge cases and ambiguous queries. Ultimately, the quality of reinforcement learning data and optimization strategy differentiates vendors' function calling implementations. Let's talk about the role of special tokens in model training. In many implementations, new tokens are introduced as call start and end markers before function calling training. These aren't just regular words. When the model generates a call start token, it switches to creating a structured command. This is crucial because it helps distinguish between natural language and executable commands, ensuring clarity and precision in interactions with external systems. Welcome to Chapter 2, where we explore what happens during inference. It all begins with calling a token and creating a JSON. Ordinary tokens take the lead, predicting the distribution and allowing the context to build. Unlike other systems, there's no separate tool selector or intent recognizer here. The model seamlessly predicts the next token from context, having learned during training when to use a call marker instead of a word. Let's explore how our system operates. The model itself never directly calls any functions. Instead, it generates what appears to be a function call as text. An external orchestrator then steps in, intercepting the output, parsing the necessary details, and executing the real API call. The response is reintroduced into context, allowing the model to seamlessly complete its task. This entire process ensures smooth, efficient function execution outside the model.
Welcome to Chapter 3, where we delve into the 4 ways function calling can fail. By understanding the underlying mechanisms, we can easily recognize these failure modes. Each has a specific, diagnosable cause, whether it's due to incorrect parameters, unexpected data types, or issues within the function logic itself. Pinpointing the root cause can help in resolving these problems efficiently. Let's explore these failure modes in detail.
Let's dive into failure modes. First, selecting the wrong tool happens when tools are too similar or training data is lacking. Next, we see errors in parameter filling, using the right tool but with the wrong values. This usually stems from unclear tool descriptions. Then, there are missed calls, often due to pre-training patterns and weak prompts. Finally, unnecessary calls occur when trigger conditions are too broad or lack negative examples. Today, we'll explore 2 dimensions of failure causes in AI systems. On the model side, focus on the quality and coverage of training data and the reinforcement learning optimization strategy, as these elements define the capability ceiling. If that ceiling is too low, consider switching models. On the usage side, prioritize clarity in tool descriptions, parameter formats, and system prompt guidance. For API users, optimizing here is crucial for success. Welcome to Chapter 4, Vendor Differences. While OpenAI, Anthropic, and open source models share the same core functionalities, they differ in details. They use unique markers like XML tags or plain text for signaling commands. Tool descriptions might be injected directly or through API fields, altering the context. Models trained on multi-call samples manage multiple tool call blocks, unlike single-call models. Lastly, APIs can force or block tool calls by adjusting token sampling probabilities. Welcome to the Interview Answer Framework. This approach helps you add depth by focusing on 4 key areas. First, consider the mechanism where next token prediction doesn't introduce a new module. In training, we use an SFT foundation with RL refinement in 2 stages. During inference, a token probability shift triggers a format switch. Lastly, assess reliability by balancing model level and usage level levers for optimal performance.
Understanding that there's no magic in the model, it's simply generating text with a special pattern, enables you to diagnose whether issues are due to the model itself or how it's used. This knowledge helps you decide when to adjust the prompt or switch models, and design robust systems with effective failure handling. Without this insight, you might treat function calling as a mystery, relying on trial and error without a clear path to optimization.
Welcome to the Optimization Cheat Sheet. First, focus on crafting clear tool descriptions. Think of them as documentation. Precision is key to avoiding mistakes. Next, include a specific example for parameter formats to significantly reduce errors. Strengthen your system prompts by clearly indicating when tools should be used, as weak signals fall short. Finally, define trigger boundaries precisely to avoid unnecessary tool activations. This ensures efficient and accurate system performance. Let's dive into the key takeaways. First, while the mechanism remains the same, the output pattern can change. Function calling is just predicting the next token, yet the model learns to output JSON in specific contexts. 2-stage training is essential. SFT teaches timing and format, while RL ensures accuracy. Remember, the model generates data, but execution is handled externally. Lastly, Diagnose issues before optimizing. Know if you need a model switch or better prompts.